It's my pleasure to introduce our next speaker, Joshy Orndorff, software engineer at Moonbeam. He will guide us in a journey to create a Substrate chain with a Ethereum compatible virtual machine using Frontier. Welcome, Joshy. I'll let you take it from here.
Thanks a lot, Ricardo, and thanks a lot, everybody, for attending. So I'm Joshy Orndorff. I work at PureStake. That's the company that's doing the technical development of the Moonbeam network. Here are some places you can find me on GitHub and on Twitter. And if you know me from any of those places, you're probably used to my face looking a little more like this. A little bit about me briefly. I was originally a physicist and I studied computational optics and photonics, trying to make these personal computers that we know and love work on light instead of electricity. Later, I became a high school teacher where I taught a lot of normal computer science, but I also started doing blockchain research with students. Eventually, I made my way to Parity, where I worked on the Substrate recipes and the Substrate seminar. If you're learning Substrate, you might have encountered some of those. And then I made my way over to PureStake about a year ago, where we started working on the Moonbeam project. Sort of concurrently with those last two, I became a dad. And this is my family and my kid. And I put a link there to his birth certificate that we put on the Kusama blockchain network. And I believe everybody should have the link to these slides as well as the code we're gonna write to follow along. So I'll briefly tell you about Moonbeam. Moonbeam is a parachain that's gonna launch on Polkadot pretty soon, as we recently found out. It's Ethereum compatible, and it uses Frontier, this library that I'm gonna teach you about, to get its Ethereum compatibility. So we've helped develop Frontier along with several others, and that's why I'm qualified to tell you about it. So the Frontier team is definitely different than the Moonbeam team. It's a superset. So you can see the lead contributor there is Wei Tang from Parity, and there's several other members of the Moonbeam team, as well as the Edgeware team, Darwinia team, and the Akala team, and lots of other people in the space. You can check out lots of contributor stats on the GitHub page. So you can see there, I'm not the main contributor. I'm not even the biggest contributor from Moonbeam. I'm just the one who's going to present it to all of us today. So you have all of these people to thank for the code that you're about to learn about. Here's a bunch of common resources, documentation for different pieces of Frontier and different ways to get in touch with the community. I'm not going to read them, but you can look over them. The first one there, you can see it's still a to-do, the written version of this tutorial. I hope to get that done soon, but what I really mean by to-do is that this is your homework. So I expect everybody to take what they learned today and make PRs to make the written version of this tutorial really as good as the presented one. Finally, I linked the Moonbeam docs because there are some things that are in our docs that just haven't made it upstream into Frontier yet. So before we start talking about the code itself, I want to spend a few minutes talking about branch management. And while this can sometimes feel like an aside, I really want to emphasize that it's critical that you do this every time and that you get it right, because otherwise you'll have very confusing and frustrating compile errors later on. So we're starting with the Substrate node template. That's this crate called our node on the top, and it depends on Substrate. And after we're done installing Frontier, we want our dependencies to look a little bit like this. Our node will depend on Frontier, which also depends on Substrate. And this is good. This is how we want it to be. A common mistake is that you start with your node depending on some version of Substrate, and then you find Frontier depending on some other version of Substrate, and you naively take a dependency on Frontier. And as you can see, you now have two different and conflicting versions of Substrate. And the error messages you'll get will say confusing things like a particular trait is not implemented. And what really happened is that a trait with the same name from a different version of Substrate is implemented. So that's the bad version. And to really drive this home, I want to show you the branch that we're going to use today. So we're looking at a screenshot I took from the GitGraph extension of VS Code. There are many good tools like this, and you can use whichever one you like. But if you don't have one you like, the link to GitGraph is right there, and I highly recommend it. And what you can see in pink here is Frontier's master branch, and in blue on the left is the branch that we're going to use for the workshop today. And you can see that the first thing I did was bump the Substrate dependency, and then I had to make some changes to make it work with the new Substrate. Typically, these changes aren't very complex, and you can use the PRs that went into Substrate as a guide, but you absolutely have to do it, or else you'll end up with the mismatched dependencies like this. You can also see that while I was working on this branch, new stuff went into Frontier, and that's why I had to continually merge the pink into the blue, and that's just a reality of how this works. And in fact, I prepared this branch about 3 days ago, and since then, new things have already gone into Frontier. So this can be part of your homework as well, doing it with the latest Frontier branch. Okay, we have a lot of code to cover today, so I'll just give you a rundown of what it's going to be, and then we'll dive in. You can see this is a screenshot from the same Git graph extension. This time we're looking at the node template. And the Substrate Developer Hub team does a really nice job of making monthly tagged releases on their node template. And I'm starting from that. You can see my branch in blue. This is all the code that we're going to write moving vertically. So the first thing we'll do is install the EVM. Then it's Genesis config, then Pallet Ethereum, et cetera, and we'll work all the way up to the top of this branch, and we'll do several demos along the way. You can also find all of this code on GitHub. The link is right here, and I'll probably show that several times as well. Here are all the exact same commits, and we're going to go through them through installing the EVM, it's Genesis config, Pallet Ethereum, etc. Okay. So let's dive in. We're going to start with Pallet EVM. This section of the talk refers to the first two commits. Here's their individual links, but you can also find them on that overview on GitHub. So this is how I like to depict the architecture of a Substrate node. There are many parts. Each one is represented by a box. So you can think of the transaction pool, your consensus, this Prometheus thing that gives you metrics. You can think of an RPC server where you can send in data like transactions or get data out like storage information. And then there's the famous runtime. And this is an advanced talk, so I'm not going to belabor this architecture diagram very much. You can see pallets here in white, like rounded rectangles. And then these parallelograms are basically just constants that exist in your runtime. Some of these will have to change. And these little scroll shaped things are runtime APIs. This is ways that parts of the node outside the runtime can call into it. And this is what's sometimes called crossing the WASM boundary. So anytime the outer part of your node wants to access the runtime or vice versa, you need something like this, a runtime API, to cross the WASM boundary. So we're going to install a new pallet. That's our first step. That's the simplest step. It's called Pallet EVM. And basically it takes this crate called the Sputnik EVM written by Wei Tang from Parity, and it wraps it in a Substrate pallet so that we can put an existing EVM inside of our Substrate runtime and execute EVM bytecode against it. This is sort of the most basic notion that you could think of when you think of getting an EVM compatible Substrate chain. If you saw the panel earlier where Alan, our Moonbeam team lead, and several other parachain developers were on there, they said they all basically use the same EVM and the layers on top of that are what differed. And so this is sort of the core part that you'll use for almost any level or design of EVM compatibility. The Pallet EVM ships with Frontier. And so to add it into our architecture diagram, we put it right here. And it's just one more pallet. So adding a pallet is something that I expect everybody's familiar with if you're at the advanced workshop. And so I won't belabor it too much. I want to dive into the code. This is a screenshot of the config trait, which you probably know is sort of like the core part of adding the pallet. There's other things too, like taking on the crate dependency and updating construct runtime, but this is the bulk of it. So let's look at the code on GitHub and then we'll come back to the slides. Here's the tagged monthly release, and then here's my first commit. This is the one we're working on. So the first thing we do is take on some dependencies. Here's one where we take on a dependency for Pallet EVM. That's the only one in this case. And up here is some artifacts of the reality that I explained earlier about having to line up your Frontier branch. When I was preparing our Frontier branch, I had to update Frontier for a new change in Substrate called scale info. You might know about that change. It's very exciting. It means we'll no longer have to manually copy and paste type metadata into Polka.js. I'm really, really excited about it, but it had to percolate through several crates, and that didn't all happen as instantly as you might want. And so we have a few crate overrides. This is a really nice technique for when you're working lower in your dependency graph and you want to use those updated crates immediately in your node. I won't say more about it now, but you can ask me questions if you have them. We do this a lot at Moonbeam when we're doing dependency updates. Okay, there's some uses. I'm always going to skip over these because I've given you guys the exact code that you can reference, and I know that you know how to use different pieces of Rust. So here's the core of it, where we implement the config trait. You can see there's a couple constants. One is my chain ID. I did 1337 just because it's a nice memorable number, and we'll use that in our demos a few times to confirm that we're actually talking to the right chain as opposed to like Moonbeam or Moonriver or Ethereum mainnet or something like that. Then there's the config trait, which we'll talk about in detail on the slides. The first few types are pretty standard. I'm sure you've seen the event type. Currency, this is basically the token that your EVM will treat as the ETH token, the native token. And here we've wired it up to an instance of Pallet balances. The next few are just constants. So there's the block gas limit. We set it to U32 max value. This is something you can tune on your chain. Here's our chain ID 1337. The block hash mapping is something that I'll talk about in the future when we have more context in a few slides. And the runner is something that you always do the same way. So these are all fairly straightforward. They're either constants or things that you can copy directly. The rest of these types are a little bit worth looking deeper into, and I'll talk about those on the slides. And the final step of this is updating construct runtime. So there's the whole commit. Okay, back to my slides. We're gonna dive in on these last 8 associated types. As far as pallets go, this is a lot of associated types. You can see that most of them I've set up to the simplest minimal thing where I just put unit, and that's a great thing to do when you're learning or when you're creating a workshop, because it allows you to typically keep moving quickly without having to get caught up on the details of each of these. So first I'll talk about these 3, then I'll talk about the next 5. So there's this concept of account mappings, and the idea is that inside of the EVM, you have standard Ethereum style H160 accounts, and they will have some data associated with them. For example, they have an account balance, and they also have an account nonce. And in the early days of Pallet EVM, those were stored directly in the Pallet, but this leads to a lot of a very noticeable and very rough seam between working in the EVM and working in all the other places in the Substrate runtime. And so Pallet EVM has now changed so that every EVM account, each one of these with the Ethereum icon, is backed by some actual Substrate account type. Now, I haven't listed a concrete account type here. It's because Substrate runtimes are generic over the account ID type. And basically, when you configure Pallet EVM, you have to specify some way to map the Ethereum counts into the native accounts. And the standard way to do it is called the hash truncated account mapping. That means you take the H160 address, you hash it, and then you take the first 32 bytes and map that to a Substrate style account ID 32, if you're using the most common notion of account ID. This is how most of the chains I know of do it. It's also how our chain that we're building today is going to do it. I want to take just a moment to point out another way that you can do it, which is the way Moonbeam does. And if you go back to our architecture diagram, we actually have changed Substrate's account ID to use a less standard, or I should say non-standard account type. And we're using the H160 just like Ethereum does. And the beauty of doing this is that our account mapping gets to be dead simple. It's actually just the identity mapping. So your Substrate native account that backs your EVM account is exactly the same account identically. There's no hashing or truncating or other interesting mapping happening there. And this is an option available to all of you too. And the features to do this come with Frontier. And if you need an example, you can look at Moonbeam's code. Okay, the next thing that we have to answer is who's allowed to do EVM execution. So if you want a particular H160 account to do some execution, like deploy a contract or call a contract or move some ETH tokens inside of your EVM, we need to know what origin can do that. So one option is to use the root origin. So this means only like sudo or democracy could cause the EVM to execute. And that's how we're doing it in the workshop, because it's a very easy way to keep moving. Another way that you could do it is to say that nobody is allowed to do EVM execution. And it might seem silly at first, like why would you have an EVM if you're not going to let anyone execute in it? One reason you would do that is as part of a phased rollout if you're not enabling your EVM yet. And another reason you would do it is because other pallets in the runtime can still call into the EVM pallet. So this is actually how Moonbeam is configured. And the only execution that's allowed to happen in our EVM is that it can come from Pallet Ethereum, which we'll talk about later in this talk. But as a reminder, our demo node today, the code I just showed you, is going to allow only root to execute in the EVM. Another option is the manual mapping, where users specify the mapping themselves. Akala designed this, and it's in use in their chain right now. It's worth looking at. I put the link there. There's also this signed truncated idea, which is kind of the opposite of the account mapping I showed earlier, where you take a native Substrate ID and you hash it and you truncate it down to 160 bits. And that works fine, but one thing to keep in mind is that it is not going to be the same account ID on this side of the mapping that is the backing account we saw in the earlier mapping, and that can be very confusing for users. So something to keep in mind if you go this way. And then another option that only exists if you have changed the native Substrate runtime account ID is to do the identity mapping again. And as you can guess, Moonbeam could have been configured this way, except we didn't do it because, like I said, we have it disabled so that you can only use Pallet Ethereum. So that's another of the associated types that you can fill in when you're configuring Pallet EVM. The ones we've talked about so far are the account mapping, and now the call origin. So the third one I'll talk about is the weight to gas mapping. The idea here is that users need to pay for the computational resources that their transactions use in order for your chain to be secure. And in Ethereum, this is accounted for by gas, which is kind of a unit that abstracts over all computational resources, whether that's CPU time, memory, storage. In Substrate, it's done differently. We use weight, and weight is specifically for the resource of CPU time. And since they do sort of measure fundamentally different units, the mapping is going to be complex. It's not as simple as finding the slope of a line. You really have to consider what kind of contracts are going to be used on your chain, and you have to put a lot of thought into it. So I cited a paper here where they start to benchmark common contract calls on Ethereum, and this is a good place to start informing your methodology for setting your weight gas mapping. For today, for a workshop, I've set the weight gas mapping to 1-to-1. 1 unit of gas equals 1 unit of weight. That means our chain is most likely not economically secure, but for learning purposes, it's perfect. The next thing is find the author. So in the EVM, contracts can ask the EVM, who is the author of this block? And you have the opportunity to provide a way for the EVM to know the answer to that question. And the way that you answer that question will depend heavily on your consensus mechanism. So here I've showed a screenshot from the Frontier template that ships with Frontier. This will work great if you're using Aura. There's another example in Moonbeam if you're using Nimbus consensus. And between the two, I'm sure you can write the right code for whatever consensus you are using. For today, this is not one of the more advanced aspects of configuring Pallet EVM, so I'll leave it as the default implementation, which doesn't return any author, because there's more interesting things that I want to show you. Next is what you do with transaction payments. So the Pallet EVM is responsible for deducting all of the transaction fees. Where those fees go after they're deducted is up to you. You could put unit there. That's what I've done today. That means they're just going to be burned. You could also use any other kind of unbalanced handler and send your fees to the treasury, for example, or to the block author or some combination. And to give you just a little snippet of what it looks like in Moonbeam, we've basically used this EVM currency adapter, which comes with Frontier, to use the same deal with fees struct that we've made for all the rest of our normal frame transactions. So this is the same thing we have wired into Pallet transaction payment. We're just wrapping it in an EVM adapter. And I would recommend in most cases, this is what you do, unless you, for some reason, want your EVM transaction fees to be handled separately. Okay, so now we have Pallet EVM installed in our runtime and configured in a way that it'll work. And we're going to do a demo. So this is Gerald. This is our demo account. Here's his address, 6BE. I encourage you to remember it so that you can easily see what's happening in apps. This is an account that we used all the time in Moonbeam development, and we're going to share it with you too. Obviously, I've put all the private information right here on the slide, so you should never transfer any real money to this account. It's not your account, it's everybody's account, but we're going to use it for our demos today. And okay, let me give you an overview of the demo, and then I'll actually do it. So we're going to deploy a contract that I've written. It's an incrementer contract, and here's a link to Remix so you can open it. I provided the HTTPS link and also the HTTP link, because if you're communicating with a local node, it may be that you need HTTP. I'm not going to get into those details. Then we're going to deploy it. Now, this deploying is done through Polkadot.js. It's not using standard Ethereum tools or anything like that yet. We haven't installed those yet. All we've installed is an EVM inside our Substrate runtime. Then we're going to read this contract storage, and then we're going to call its increment method, and we're going to see that it actually does the computation we expect. So what we're going to see here is what you can do with only Pallet EVM, none of the other fancier compatibility pieces that ship with Frontier. So let's get this thing going. I'm just going to copy the link real quick. And that link should open the exact code that I'm going to use. This is, there it is. There's 3 files, and we're dealing with incrementer.sol first. I won't dig into the code too much. I'm sure you can read it. Basically, there's 2 storages, the value and the person who called the account, or who called this contract last, and there's a function called increment, which adds 1 to the value and stores your account. There's a few others that do exactly what it sounds like they do, and I'm not going to read them. So we can compile this like we always do in Remix, and it gives us all these compilation details. Now, normally what you would do if we were using Moonbeam or Ethereum or something like that, we'd come over here and deploy it, but we don't have all those RPCs set up, at least not yet. So what we're going to do instead is dig in here and get the bytecode. And here it is. It's this thing that starts with object, and it's really long. So I'll just select all the way to the end. Okay, that is our compiled EVM bytecode for our contract. And now I'm going to deploy it. So here's Polkadot.js apps, and you can see I'm not connected to a chain. So I'm going to start up the chain that we just coded. And there's my command. It's just target release node template, and then I give it the --dev option, which will just start a single node that authors blocks, and --temp, which means create a new temporary data directory so that I don't accidentally use any old data directory that I had before. Okay, and there we go. We see a block got authored and apps came to life like it always does. We've got 4 pre-funded accounts here. Yeah, it looks great. So let's try to deploy our contract. You might remember I said to execute EVM code, we have it set so that only root can do that. That means we need to submit a pseudo transaction, and we're going to submit it to the EVM pallet. We could call. We're going to do that shortly if we had a contract to call, but now we don't. So we either need to create or create to. Either one of these will work. I'm going to use create to just because then I know what the deploy address will be. So here's where we paste our bytecode that we got from the Solidity compiler. Here's where we say what account is going to call this. And you can get that information from the slides. I'll copy it right here. All right, so we're deploying from Gerald. We're deploying this contract. The salt is just a number you can enter that affects your final deploy address. I'm going to leave it at 0. Value, we're not sending any ETH. Gas limit, I will send like 1 million, I guess. That's plenty. I don't know how much we need, but not that much. And gas price, we configured that to be 0 when we configured our fee calculator to 0. You should never do that for a real chain, but again, for learning purposes, it's fine and an easy way to go. So let's try to submit this transaction. It might take up to 6 seconds for our Aura block to get authored. Okay, it says it's in the block. No errors here, no errors here. So it's probably good, but we want to really understand what we did. So let's come over to our chain state tab, and let's look at our EVM chain state. And what we can do now is there's 2 storage items. We could look for the account storages or the account codes. Let's look at account codes first. And if you put an option here, it'll tell you the account code for that specific contract. But if you don't include the option, it will tell you the account code for every contract. So we see 3 things here. Let's go over them in order. This is our one that we just deployed. You can tell because it has our bytecode. It's the only one that has any interesting bytecode. This is 6BE. That's our Gerald account. There's no code there at all, but it exists because there's a balance at that account. And here's one at a very strange address, all the way at the 6 address. And that is from a pre-compile that I haven't told you about, but that I'll tell you about later in the workshop. So what we can see is this is our contract address right here, 07CB something. So I'll copy it. While we're here, let's look at the account storages. Now we do have to provide a specific contract address. So I'll provide ours. And we could provide a specific storage address, but I'm going to say, tell us about all of the storage in this contract. Okay, and it shows us that nothing's there. That makes sense. We just deployed this thing and we've never put any data in it. So what we want to do now is actually interact with our incrementer contract. So let's try that next. I'm going to go back to the pseudo tab. Every EVM transaction for now will be a pseudo. This time we're going to call, and we're going to call the contract that we just deployed. We're going to call it from our Gerald account again, which is this guy. And then, okay, so now the input bytes, we need to know what method we're going to call. If you're familiar with Solidity, you'll know about the 4-byte function selector convention. And we can get that from MetaMask as well. by coming here and looking at function hashes. And we're going to call our inc method, and here is its function selector. So I'm just going to copy it. And what you can take away from this is that everything in the EVM is there, it's working, but it's a real pain in the butt to use because we have to copy raw bytes all over the place. And as we move through this workshop, we're going to make that better and better by adding more and more real Ethereum compatibility. I'll just use 1 million for my gas limit again. And we'll submit this one too. Okay, says it's in. So let's go back and look at our chain state again. We wanted to look at the EVM, and we wanted to look at the storage for this contract that we just deployed. And we'll look at all of its storage items. Okay, so they all start with our contract address. That's good. That's how double maps work. And there's 2 different storage items. The first one contains this value that starts with 6BE. Remember, our contract stores the last account that called it, and that's our Gerald account. And the other storage item is a value. It's just the value 1, and that's because this is an incrementer, and we just incremented its value from 0 to 1. So to recap what we did in this portion of the demo, we compiled a Solidity contract using Remix. We deployed it. We read its storage, saw that there was no storage. We called its increment method using the 4-byte function selector we got from Remix, and then we read its storage again and saw that the increment method worked. So we've now officially deployed and executed EVM bytecode inside of our Substrate chain. Congratulations. There is one more commit that I was gonna talk about. Whoops, what happened there? Anyway. So that was installing Pallet EVM. I'll briefly cover its Genesis config, because if you had actually tried to compile this commit right here, the runtime compiles perfectly, but the outer node doesn't. It says you need to set up the Genesis config for the EVM. I'm skipping uses, like I said. Here we go. This is where we're configuring it. You know, this is the bottom of our chain spec file, right below where we configure every other pallet. And there's a single thing you configure. It's an item called accounts. So we make this mutable map of accounts and we add one. And here's where we've configured Gerald. That's the address you might remember. We've given Gerald a nonce of 0. That's the standard way to start your nonce. We've given him a balance just so we had some funds. And then this is not a contract, so there's no code or storage. So that's how you do an EVM Genesis config. Okay, back to the slides. Now let's talk about Pallet Ethereum. This portion of the talk is going to cover the next 3 commits where we install Pallet Ethereum itself, and we modify our notion of unchecked extrinsic. So if you saw the last talk, this is touching some of the same parts of the code that they touched there, although admittedly in a less drastic way. Then we're going to actually install the pallet itself, and finally, we're going to update our Ethereum block hash mapping, which I'll explain when we get there. So here is our architecture diagram. We added Pallet EVM before. You can see now that we're adding Pallet Ethereum right here. And we're going to modify this notion of unchecked extrinsic, this piece of the runtime that existed there all along. We're now going to change it. So let me explain, before we look at the code, let me explain a little bit about what Pallet Ethereum does and what it's for. In fact, I'll leave this slide up. So Pallet Ethereum is going to allow us to send Ethereum formatted data to our chain and receive Ethereum formatted data from our chain. That means we're no longer going to have to copy paste bytes like I just showed you how we were. Instead, we'll be able to use normal Ethereum encoded transactions. So this diagram here is taken from a different talk I gave in Substrate seminar. That was a deep dive into the structure of a Substrate block. And if you're curious about this, I highly recommend that talk. It's linked right up here in the header. What it shows is a blockchain. You can see blocks 1, 2, and 3 going down the middle. Those are actually the headers. It shows all the fields that are in the header. Off to the right is the body of the block, which is basically just a fancy way to say the list of all the extrinsics that are in it. And off to the left is the state that's associated with each block. And the state contains all the data that gets stored in your runtime. So for example, who's the pseudo key? What's the timestamp? All the different balances. The EVM stuff that we just saw would also be stored in the state, although I haven't shown it here. And when we add, so this is basically how your chain looks before we've added Pallet Ethereum. And when we add Pallet Ethereum, we're going to add something to each section of this diagram. So let me show you one at a time. The first thing we do is add an Ethereum style block into storage. So if you think about Ethereum mainnet or Geth or anything that's Ethereum related and not Substrate related, and you think about the way that those blocks are encoded and the data structure that you consider a block, we're going to store exactly one of those blocks, Ethereum style encoded, inside of our runtime. That means that when you call up an RPC endpoint and say like, hey, tell me block 55, it can tell you an actual Ethereum block, not just Substrate's version of the same data, but an actual byte-wise compatible Ethereum block. So that's one of the things. The second thing it adds is a digest into the header. So this is something that happens at the consensus layer and something that you might not have seen before in an intermediate workshop. Your Pallet Ethereum in your runtime will add one of these digests into the header of every block. And the header is the most fundamental part of the blockchain. Even the light clients will sync it. And this is important because this digest contains the Ethereum style block hash, because you're really going to need your block hash to be there in your header. And it also contains all of the transaction hashes, which are used later on in a piece of the node called the mapping sync worker that I'll talk about when we get there. Finally, we add one extrinsic type. It's called transact. And this is a transaction that allows you to submit unmodified Ethereum encoded and signed transactions. So think about the bytes that come out of MetaMask when you send a transaction to Ethereum. You can submit those bytes to this extrinsic and it will execute them in our EVM. This extrinsic is why I said that Moonbeam's EVM is configured so that no one can execute in it, because all of the execution we're going to do is going to come through this Pallet Ethereum transact extrinsic. This is a really good idea if you're striving for full Ethereum compatibility, because any execution you do of, directly against the EVM will not be indexed in Ethereum style block explorers. But anything you submit here to this transact extrinsic will go in this Ethereum style block and will be indexed by those explorers. So for example, if you ever heard of like Block Scout or Etherscan, those tools can actually work with Moonbeam because we force everyone to transact this way. Okay, so I want to look at the code before we go on to any more slides. So we already looked at Pallet EVM and its Genesis config. Let's look at Pallet Ethereum. We take on some more dependencies, one for Pallet Ethereum and one for FP self-contained. This is the crate that contains our new unchecked extrinsic format. Here we have Pallet Ethereum's config trait. This is quite a bit simpler than Pallet EVM's. There's almost nothing interesting. State root, I recommend you use intermediate state root. I think that might even be the only option. Basically, this allows, I'm not going to dive into the details, but basically this guarantees that every substrate block will have a unique Ethereum block. So there's no chance you'll have identical Ethereum blocks in two different substrate blocks. Without this, it would be possible for that to happen with a very low probability, but now we've made it cryptographically impossible. Okay, so finally we update construct runtime, nothing too exciting there. Now here's the small but mighty change where we change our unchecked extrinsic format. So you can see we've switched from the generic format to this FP self-contained one. And you can also, that's actually all you can see on that line. And we have to implement a trait that works along with this self-contained unchecked extrinsic format. It's called self-contained call. And we implement it for the outer call struct that construct runtime generates for us. Okay, and basically it does this. You can see the same kind of code in each one of the functions. We basically check if this call is a Pallet Ethereum call. And if it is, we dispatch it using the self-contained logic. And otherwise, we just dispatch it using all of the same normal frame logic. So all of these things are just wrappers. They say, if this is a Pallet Ethereum transaction, then do the Ethereum stuff. Otherwise, pass it on to all the normal mechanisms that are wrapped inside of this struct. That's all I'm going to say about that, actually, and that's the entire commit. Okay. The next commit is the Genesis config. This one is dead simple. There's nothing to even configure here. There's no data you have to enter. There's no opportunities to type the wrong data, but it is critical that you include this line. And the reason that we have to do this is because I already mentioned that we have an Ethereum block mapped in storage of every substrate block, and we want that to also be the case for the Genesis block. We want the users of Ethereum tools to be able to call up our chain and say, hey, chain, please tell me about block 0. And if we don't have this Genesis config here, we won't be able to map our Ethereum style block in block 0. So that's all there is to it. Where was I? Oh yeah, right, okay. And then the last one is switch to Ethereum block hash mapping. This is something that when we first installed Pallet EVM, I said, we'll talk about this later. Now we're gonna talk about it. So this is the core change. This is part of Pallet EVM config. This is code that was already there before we installed Pallet Ethereum. And it has an associated type called block hash mapping that we haven't talked about yet. And I've switched it from Substrate block hash mapping, which is what we started with, to Ethereum block hash mapping. So let me tell you what this associated type does. The block hash mapping allows EVM contracts to call the EVM and say, hey, EVM, tell me the parent block hash or the grandparent block hash or the block hash from 100 blocks ago. And I think you can do that for 256 most recent blocks. And Pallet EVM needs some way to give data there. One way you could do it is just to make it always return 0. That's the simplest and least useful way. Another way you could do it is to look at the block hashes of the previous substrate blocks. That's better because then you at least get some pseudo entropy that you could use there. And the best way that we're now doing is to actually use the parent Ethereum blocks hash. Now, this wasn't possible before we had Pallet Ethereum installed because we weren't actually encoding Ethereum style blocks until we had Pallet Ethereum installed. But now that we do have it, we can go back and change Pallet EVM's config so that we use those Ethereum style block hashes. And in that way, we've gained one more little bit of real, genuine Ethereum compatibility. Let's go back to the slides. Okay, right. So I talked about the block hash mapping. We switched from this one to this one. That's the commit we just looked at. Okay, let's talk a little bit more about this unchecked extrinsic thing. And actually, you can see it. You can see the differences more in the checked extrinsic struct, but the one you have to change in the runtime is unchecked extrinsic. So on top, we have the generic substrate one that almost every chain uses. And on the bottom, we have the Frontier self-contained one. And you can see they're nearly identical. They both have two fields called signed and function. Function contains the call, just exactly the same in both cases. What changed is signed. In the standard checked extrinsic format, you have an option where you either have some account ID and extra. That's the case if your transaction really is signed, then you have the account ID that signed it and the extra signed data. Or you would have none, which means it's an unsigned transaction. Here we've changed it. In Frontier, we've changed it to use this fancier thing called checked signature, and I'll show it to you right here. Checked signature, remember, we're replacing an option with this thing, and it's very similar. Here we have signed account ID extra. That would be exactly the same as some in the option case. Here we have unsigned. That would be exactly the same as none in the option case. And the third variant is the new thing. This is called self-contained. And this is where our Pallet Ethereum extrinsics are going to fall. And they're signed, but they're not signed in the standard substrate way, where the extra information, such as like the parent block hash or the longevity or something, those aren't separate. And while we think that the way Substrate designed this, with those being separate, is a really good design, we can't go back and change the way they did it in Ethereum and still maintain compatibility. So for compatibility, we've added this extra variant called self-contained, which knows how to handle Ethereum signed transactions. In previous versions of Frontier, we jammed these Ethereum style transactions into unsigned transactions, and that worked okay. In fact, Moonriver launched with that way and it worked just fine, but it does incur some extra complexity and some performance penalties. And so this is actually an idea that was inspired by Brian Chen, XLC from the Akala team, which just goes to show like how many different people are working on and contributing to Frontier. Okay, so we're going to do a demo again. This one's not going to be quite as impressive as the one for Pallet EVM, but we'll just take a quick look around and see some of that stuff that I said Pallet Ethereum would add. So let's start by looking at some of Pallet Ethereum's storage. Oh, we're on chain state already. All right, Pallet Ethereum. I'll close this out. Okay, yeah, so one thing that we can do is just look at the current block. This is probably very telling. So this says that block number 181, this is the Ethereum style block. And you can see all this Ethereum style stuff, like they're talking about Aumers. That's an Ethereum concept. And this field is called beneficiary instead of author. That's an Ethereum style concept. Here's a bunch of gas stuff. So this really, really is an Ethereum style block stored in Substrate storage. And whenever an Ethereum style tool calls asking for this data, this is what it's going to get back. There's some other storage here that's a little bit less interesting to see, but I talked about the block hash mapping, for example. We can see the most recent several block hashes are all mapped here. Okay, I also told you about that log that got added to every block. So when you look at a block in apps, you can see all of its logs. And pre-runtime and seal, those have been here always. Those come from Aura. I did not add those. Those were with the node template. But here's this one that comes from Frontier, Consensus Engine Ideas, FRON. This is the one that contains all of the Ethereum style block hash and transaction hashes. So that's new with Pallet Ethereum. And then the last thing I'll show you is on the extrinsics tab, we have Pallet Ethereum Transact, and that's the only one. Now I'm gonna save us all the pain of sort of like reverse engineering the bytes that come out of MetaMask and pasting them in here, but it can be done. And if you really want to dive deep, I encourage you to do that because you will learn a lot. But it's gonna take some patience, I can say that. Okay, so there's a look around of what we got with Pallet Ethereum. Now that we have Pallet EVM and Pallet Ethereum, so we have the execution environment, the virtual machine, and all of the Ethereum style data, let's start plumbing the RPC layer. So that means we're going to start working outside the runtime to connect that information that's in the runtime that we just set up with tools that will call up via RPC. So think of tools like MetaMask, for example. And there's two commits here. One of them is prep work. It's called adding the runtime API. And the other one is adding the net API RPC endpoint. So the net API is the simplest Ethereum style RPC endpoint. And because it's simplest, it's the first one we're going to do. As always, here's the commits on GitHub. Let's look at our architecture diagram. Can you see what's new this time? No new pallets. This is what we're adding. The Ethereum Rpc API. This is a runtime API. This is a way for the data that I just showed you that's stored in Pallet Ethereum to cross the WASM boundary and get back out ultimately to our RPC server. And that's what we're going to modify in our next commit, which I'll show you right here. In the next commit, we'd add the net API, which goes in the RPC server. And so the way this works is that MetaMask sits outside the node here somewhere, calls up to the RPC server, to one of these net API endpoints, and the net API reaches in through the runtime API into Pallet Ethereum, where it grabs the Ethereum style block or whatever it is it's asking for, and then the data goes all the way back to MetaMask. So that's kind of the pipeline we're working on. Let's put this piece of plumbing in right now, and I'll do it by showing you code. Oh yeah, where's the code? Here we go. Yeah, so we're up to this one. Hooray, we're chugging right along. Add runtime API. So we start by taking a new dependency, FP RPC. These are the frontier primitives. This is kind of named after the SP, Substrate primitives convention. Frontier follows that also. A bunch of uses. This is all inside of our runtime, I should say, runtime source lib. And here it is. We're down at the very bottom of the runtime inside of the impl runtime APIs macro, which we talked about in the previous talk. And we're adding a new one. This is the API that we got from FPRPC. That's why we added this dependency. And it has several methods. Some are simple, like chain ID. This basically just returns a constant. Some of them are less simple. This one called account basic returns information like your balance and your nonce and etc. You know, account code. This is data we looked at already. We saw the account code, the byte code that was associated with our incrementer contract. But what this function does is allows that data to cross the WASM boundary. So I'm not going to look at all of these. One of them is call. That's the one that actually lets you make calls. This is the thing that will get used when you call the increment method, but it wasn't for us because we went directly through the pallet. And it's long. There's several methods, but the implementation is pretty straightforward. I think you can basically copy paste this exactly as it is into almost any chain, and you'd only have to make a few minor changes in variable names and stuff. And that's it. It's all right in the runtime. It's all this. And by pasting this code in, we've basically created that gateway for Ethereum style data to cross the runtime barrier, the WASM barrier. So, okay, that prep work is done. Now let's install the net API. And this part happens at the RPC level. So if you're familiar with JSON RPC, this should look familiar. All right. So here we are in the...
Okay, Joshy.
So I should... yeah, go ahead. Hi, Ricardo.
Hey, just a few questions here. So yeah, we got a few questions from the audience. Like one is like if changing all this format, changing like really how the block is grabbed using all the EVM, does that really makes using original Substrate tools like much difficult to use, or like it's compatible? Or
Yeah, that's a really, really good question. So many of the things that I've shown so far and will continue to show are additions rather than changes. So specifically, the part of the talk we're on right now are additions. So those things don't make the Substrate tools harder. Some of them are changes. So for example, the unchecked extrinsic format. Now, in our case, we're really lucky because we changed that in a not that significant way. We just added a third variant to the end, which means it's actually binary compatible with the old one. So we got lucky there. Normally that would add a little bit of a headache, but in our case, it didn't. And in terms of what I've shown so far, those are all the changes. But I will say one thing that Moonbeam did, I already mentioned this, was we changed the account ID type to use H160. And that's one of those things that in principle shouldn't have made tools any harder, but in practice, every other Substrate chain at the time used the standard account ID type. And so a lot of off-chain tools assumed that all of our stuff was going to do that. So think about Substrate style block explorers, think about like Polk assembly, even to some extent Polka.js apps. So those things all had to be generalized to be as general as Substrate. And now that they are generalized, they work fine with Moonbeam, but that definitely was a bridge to cross when we got there. That's a really good question.
okay, yeah, related to that question, like if we want to use like some block explorer, I know that for example for Ethereum it's compatible, as you were explaining right now, it's compatible with Block Scout and probably other open source Ethereum tools. But like also, do we need to input all the types, or how can we make it compatible with, let's say, yeah, Polkascan, Subscan, or yeah, just make
Yeah,
it,
good question. Yeah. So most of our work has been trying to get the Ethereum style ones to work, and that just means making sure that Frontier is perfect in every way. So for someone who's going that course now, that part will actually be relatively easy. In terms of getting, yeah, like Subscan to work, for example. So Moonriver does have Subscan, and you can check it out, and it works really, really good, as Subscan always does, for balance transfers and like our parachain staking and all our normal Pallet stuff. And it also works well in some sense for Pallet EVM and Pallet Ethereum, but the limitation is basically that it looks a little bit more like that first contract deploy demo I did. All the info is there. There's nothing you could want to know that it can't tell you, but it's not a very user-friendly format. You're more looking at like bytecode and raw account addresses as opposed to like identicons and stuff. And so we are working with Subscan to sort of like add support there. There's no like fundamental reasons that can't be done on Subscan, but kind of like I explained about, Polka.js, like it's just something else that you have to do and have to get done. And so if your chain is, if EVM is one of many things that your chain does, that might not be such a big deal. But for Moonbeam, EVM is the thing we do. There's other stuff on the side. We have staking and we have governance, and those are important. But definitely EVM is the core of what we do. And so, the default view there is still has some room for improvement. And I think like it's good to be eyes wide open about the opportunities that you'll have to improve other tools in the ecosystem when you start varying from the standard in terms of Substrate. And it's cool because Substrate is flexible enough to do all of this and that, customize every single part you want. But every time you do it, you do have to make a decision like that. How much am I committing to also customizing off-chain tools? Yeah, good question.
yeah, I agree. Thank you so much. So let's get back to you.
Yeah. Cool. Thanks a lot. One other thing I'll say on that point is that at Moonbeam, we've made the decision that whenever we do have to make some customizations like that, we will make them on the Substrate side, which is to say, however Ethereum does it, that's how we're going to do it so that we can maintain full Ethereum compatibility. That's obviously not the right choice for everyone, though. That's only the right choice if your goal is to be 100% Ethereum compatible.
Awesome.
So, okay,
thank you.
Thanks, Ricardo. So just to reorient, we just added the runtime API, and now we're in the RPC layer. We're going to add this net API. Okay, so we are outside of the runtime now in the code. This is rpc.rs, and we're going to see service.rs later. So if this is your first time really sort of getting your hands dirty outside of the runtime, congratulations. This is a fun place to hack. So after all of our uses, there's this struct called full deps. This is like all of the dependencies that you'll need for a full client's RPC endpoint. And there are several of them here already, and we're adding one called network this time. So let me explain it this way, actually, because the code is too ugly to really dive into at this stage. We're going to see a lot of trait bounds and a lot of different fields getting added. And basically what all of those trait bounds and fields do is they express things like the following. In order to use the net API, you have to have this runtime API installed. And you need to pass a struct that implements this runtime API. So whenever we're adding trait bounds inside of rpc.rs, that's the kind of stuff we're expressing. Hey, this only works if Pallet Ethereum is installed. And hey, you can only use this if you have the right API there. And if you take, if when you're in developer mode, you can take time to understand all those trait bounds. But in 90 minutes, we have to skim it a little bit. But like, here's just a classic. This is an easy to read one that says you have to have the runtime API, etc. Okay, so we've added this one field we need. We've added our trait bound and a few other trait bounds that are important. And then finally, the node template makes this really clear. It adds a few core RPCs. This is like the core one and the transaction payment one that I showed in my architecture diagram. Here's the one that we're adding called the net API server. And it's really easy. You just take this thing called IO, you extend with the server that you're trying to use, and then you provide whatever fields it is that that thing needs. So it turns out the net API needs a view of the Substrate network, and that's why we had to add network as a parameter up here. Okay, so now that our RPC handler is set up to have the network and include this new endpoint, the last thing we have to do is just modify our service. So here's service RS. This is, in my opinion, really the core of a Substrate node. It's what stitches together all the different asynchronous tasks. And you can see we didn't change much here, but we did get a handle to the network and we did pass it into the full depths where we didn't do that previously. Okay, cool. So we've now added this runtime API and this RPC endpoint. And so I have a couple of example queries that we can make. And these queries are pretty simple. We can ask for things like the net version, the peer count, and whether we're listening for transactions. We can do them by curl. I put the example ones there, but we can also do them from apps, and it looks a little nicer from apps. So I'm going to show you that way. So there's this RPC calls tab over here. And the one that we just added was the net API. And it has a few methods. So in fact, those are all three of them. So let me just show you what those say. Are we listening? True. Yes, we are. What's our peer count? No peers. That makes sense. I'm in a dev node. There's only one node, so it doesn't have peers. Version. Hey, look at that. That's our chain ID number. So that's great. We now see that the net API is working. And it seems like another little thing here since I'm still doing this from apps. But one important thing to realize is that this is an Ethereum style RPC endpoint. Apps is submitting the same bytes that MetaMask does when MetaMask talks to Geth. So that's, in some sense, this is our first win in terms of byte-wise Ethereum compatibility all the way to the RPC layer. But net API is small and not that interesting. So let's get on with the real one, the ETH API. And this is the one where you can submit transactions and check storage and all of the sort of, more core tasks. So we have 2 prep work commits, and then we'll finally add the ETH RPC. And adding the ETH RPC is going to look very similar to adding the net RPC. And so most of our talking points here will be about the prep work. So let's look at the architecture. The first thing we're going to add is a little bit of code in the runtime. It's called the transaction converter. It's basically a very, very simple piece of code that takes the Ethereum style bytes that will come out of MetaMask for a transaction, takes the exact Ethereum style bytes, and it wraps them in a call enum that says, hey, this thing should get dispatched into Pallet Ethereum's transact call. And that's all it does. It's just a little bit of glue code. In fact, here's the code. I'm not even going to show you guys on GitHub because it's so simple. So in your runtime, you make a struct transaction converter, and then you implement this trait, convert transaction, and you do it for the unchecked and for the opaque unchecked extrinsic. And it's really simple. So you can see here we get in this transaction and we give back out the exact same transaction, but it's wrapped in a call enum. And that's it. And there's a little bit of scale encoding when you do it for the opaque one, but that's all there is to it. Okay, so the next piece we're going to add is, what was it? Oh yeah, the mapping sync worker. That's this guy. Okay, so we saw already that in every substrate block, there's now an Ethereum style block. And so all the Ethereum style data is there. But if you think carefully about it, that mapping is the wrong direction from what we really need. Because what we expect is for Ethereum style tools to call up our RPC and say, hey, tell me something about this particular Ethereum transaction hash. But currently our mapping goes the other way. Our mapping goes from Substrate information to Ethereum information. And so the mapping sync worker is there to create an inverted mapping so that we can sort of go bidirectionally. So to say a little bit about this, well, I put some links here. These are the docs that you can read in detail in Frontier's REST docs. Here's the pull request where the mapping sync worker went into Frontier. And then I made these diagrams that aren't displaying quite as beautifully as I hoped, but they will communicate the schema at least. So we're mapping we have basically two different storage items that we're mapping here. One maps from each Ethereum block hash to the corresponding Substrate block hash. And that way, when someone calls up saying, tell me information about this Ethereum block hash, we know the corresponding Substrate block hash so that when we call into the actual block database, we can give it a Substrate block hash that it understands. And then down here, we have a very, very similar thing for transactions. But the difference is that instead of just mapping from an Ethereum transaction hash to a Substrate block n index, instead we're mapping to a VEC of the block n index. And the reason that this is important is because of reorgs. It's possible that you build a chain and then your chain reorgs and the same transaction makes it on both sides of the fork. And so in that case, you'll have the same transaction hash mapping to multiple different blocks. And the RPC layer is smart enough to only tell you about the canonical one. But of course, in order to do that, it needs all the data available. So I also illustrated that in this catchily titled slide. You can see like the Substrate blockchain on top. Here's block n, n+1, and then at n+2, there's a fork. And whenever that happens, that guarantees that there'll be a fork in the Ethereum blockchain as well. So that's why we have to have a one-to-many mapping for transactions. Okay, right. So let me look at the code, and then I'll show you what we can call as a demo. So here's the transaction converter. I actually showed you this on the slide already, but there's the exact same code. That's literally all there is to it. Next is the mapping sync worker. Okay, so now we're getting really deep in the service. We add two dependencies. One is for FCDB, so that's for the Frontier client database. We're actually adding an entire secondary database. In addition to the normal Substrate database that stores all your block and transaction information, we're adding another one that will store those Ethereum style mappings that I just explained. And then obviously we're gonna add the crate that contains the mapping sync worker. A bunch of uses. Okay, so here we are in our service. We add a few helper functions. One tells us where the Frontier database is gonna live, and one is a utility for opening that database. And by the way, the only real thing we get as a demo after we install the mapping sync worker is that I'm gonna show you this database directory, and we can see that there really is data being written in there. Okay, so this new partial thing, I'm not gonna go through like all of what this does, but it starts to set up the core components of your blockchain node, basically. And there's one new thing that it's gonna have to do now. It's gonna have to return an ARC handle to the Frontier database. Here's where we open it with our helper function, and then here's where we add it to our return values. Okay, and then here in new full, this is when we're actually spinning up a node. We call the Substrate task manager. So this is basically a convenient handle to a Tokyo task manager that's gonna manage all of the async workers that I've shown. So let me show you the architecture diagram again. If you think about like the TX pool and the consensus workers and all these things that just sometimes seem like they're swimming around here, these are all async workers that are handled by that task manager. And we're adding this new one here now, the mapping sync worker. So we say, you know, spawn one, no surprise, we're gonna call it this. And then here's the struct we imported, and we just give it all of the fields it needs. So one thing I call attention to here is the sync strategy. I've included normal. That's what you should do in most contexts. But I will say, if you are a Cumulus-based parachain, Cumulus does some special things where it imports blocks multiple times, and only the second time is that block marked best. And that can confuse the mapping sync worker. So long story short, if you're doing this in a parachain context, you should put sync strategy parachain right here. All the other stuff that you give it is pretty standard. We're just saying, kick off the sync worker every 6 seconds. So actually the way it works is it gets kicked off every time we import a new block and every 6 seconds, just to make sure there's no long lags. Okay, so that's the mapping sync worker. Let me just do the kind of not that impressive demo, but I'll show you anyway. I've got my node still running in the left terminal, and I'm going to change directories into my temporary substrate working directory. Oh yeah, chains. Okay, so here's my dev chain. And we can see here's our normal database. That's the one that contains all the blocks and transactions and everything. The key store is always there, and the network one that contains like our peer set and some other stuff that I'm not really an expert on. Here's the new one, the frontier directory. This one doesn't exist when you just have the normal substrate node template. So I'll just show you what's in there, a database directory, and then some, some RocksDB files that look exactly like the ones in your DB folder. So this shows that we really are creating those Ethereum mappings that I told you about and storing them on our file system. All right, let's move on. Okay, yep. So there's a typo, ETH API. We're gonna add our next actual RPC endpoint right here. It's gonna, as I mentioned, it's gonna look very similar to when we did the net API, but we'll still look at it because it is a little bit more complex. So let's go see that code. Here it is, ETH API. All right, we're back in our rpc.rs file just like before. We have some new uses. We're adding some new fields to the full deps. So you might remember network. This is the one that we added before. And here are even some new ones. Here we have the whole frontier backend, so that's obviously an important one. We got some more trait bounds. Oh yeah, this I got myself confused. So this happens sometimes. We have arcs or like reference counted references to all of these various node parts like the pool. So sometimes you'll have to go back and add clones onto earlier uses so that you still have ownership of these things later on. So here's the line that's analogous to when we added the net API. We just extend with our own server and we give it all the stuff it needs. Well, this one needs a lot of stuff. Some of these ones we added as fields and full deps, and some of them we create right here. And some of these are just optimizations. So for example, we talked all about how this endpoint is going to call into our runtime API to fetch data. Well, it turns out there's some overhead associated with the runtime API, and you can work around that by reaching directly into the storage backend. It's advanced, it's complex, it works really good. And if you want to do it, this is where you set it up. But for now, we're not going to set that up because it's just for performance. There's also a thing where part of this API will actually allow you to sign transactions, which is not something you should do on public production nodes, but is something that's useful for local dev. But again, for the sake of sticking with the sort of most core ideas, I've just not done that. And then I've just hard-coded a few parameters here. For example, like how much block data we're going to cache and how much, what the limits we're going to put on our RPC queries could be. So in Moonbeam and in your production chain, something like this should probably be passed all the way back to the command line so that the node operator can control it. But that's not really what we're trying to learn today. So I just hard-coded it. And, and then there's the part inside of service.rs, which is just like before. We're going to have to pass more things to full deps. So we just create references to those and we pass them. And that's it. So with that, by the way, here are links to more details about the storage overrides for that optimization and the signers if you want to sign transactions. Each of these had their own pull request, and with many things in Substrate ecosystem, the pull request is some of the best documentation. So those are linked there. I think I meant to delete that slide. Okay, so we're going to do another demo now, but this time it's going to be way better because we now have all of the endpoints that we need to actually connect MetaMask, a straight up Ethereum style tool, to our running chain. So without further ado, let's do that. And you can see I listed the default RPC endpoint right here. So this is just a Substrate endpoint. It's always 9933. The thing to remember is that you need the HTTP endpoint and not the WebSocket one. So don't put 9944 by accident. Yeah, okay. Let me just do that demo. So here's my MetaMask. I'll unlock it and then I'll expand it. Okay, there we go. And then I will say, I've rehearsed this several times, so you can see there's a bunch of transactions in here. Whenever you're like restarting with a new chain, you have to reset your account so that MetaMask doesn't get confused. So I'm just going to do that real quick. Okay. And so now it should be good. And we're connected to this 1337 local. So, okay, so everything's great there. Maybe we'll just try to send some tokens. I don't know what address this is, but we might as well use it. And I guess I'll just send like 1 ETH. Gas price, we don't have to put anything, remember, because we configured that to 0, and I'll just leave the default options. And let's see what happens. So I'll tell MetaMask to send it. I think that's sent. Oh yeah, so now we can go look back at Polkadot.js. And what I'll do now is look at our chain state. And I actually don't think I showed you this earlier, but oh, hey, look, it's confirmed. So we'll just make double sure that that's true here on our sort of like, to me as a Substrate developer, I feel like this is my more like native tool that I trust more. So we'll just check there. Anyway, we're going to look at all of the accounts on the system, and it'll show the balances. So what we're going to see here, you might remember earlier in the talk, I talked about the account mapping from the H160s to the Substrate accounts. So these are all Substrate accounts. And some of these are pre-funded. So we have like Alice and Bob, for example. So these two are Bob accounts. You can tell by this is like the default amount for those accounts, 1152 something. Okay, here is an account that doesn't have any balance. So this I'm going to say is our contract that we deployed earlier. Here is another default frame account. Here, this one, look at this. This one has 1 ETH with 18 decimals. So this must be the 1 ETH that we just sent from MetaMask. This one is the account that we just sent from. You can see that its nonce is up to 3. That's because we deployed our contract, then we called its inc method, and then we sent ETH just now. So that's 3 transactions. And then you might recognize Alice. She's still totally unmodified. So this is the biggest thing we've accomplished so far, is being able to actually send ETH tokens with a standard Ethereum tool, MetaMask. So maybe I'll pause here for a sec for questions before I move on to pre-compiles. Have you got any, Ricardo, or shall I continue?
Yeah. Okay, so yeah. Thank you, Joshy. This looks really, really nice. So you were also like, I have a few questions here, but I also want to talk about the precompiles.
Okay.
But yeah, before getting to the precompiles, let me ask you this question. Like, is Frontier or Moonbeam possible to be more sufficient than Ethereum doing Ethereum stuff? If not, what are like the potential bottlenecks or caveats that are unavoidable?
Oh yeah, that's a good question. So Frontier, if there are limitations like that in Frontier, it's only because it's still in development. The goal for Frontier is definitely to do everything as well as Frontier can, and possibly better. Although I don't know if that's an explicit goal. So Wei Tang, the actual author of Frontier, has this idea called wrapper blocks, which I linked very early in the slides on the like useful links slide. And he explains a way that you could use Frontier and Substrate to actually create a full ETH 1.0 compatible node that could join mainnet. So for sure, Frontier strives to do that. When you talk about Moonbeam, now we have additional constraints imposed by the fact that we're a parachain. So for example, our block time is basically dictated to us by the relay chain, and the amount of execution time in each block is also dictated by the relay chain. Now, those numbers are improving all the time, and they're, as we learned recently from Gav with, or maybe Rob yesterday with contextual execution, they're about to get way bigger, and they're probably going to be higher, or at least as high as Ethereum. But the fundamental rule there is like any time that you have a more sovereign chain, like the relay chain, that's dictating some parameters of your network, we can never say unilaterally that we'll be able to do everything that that Ethereum does. And then I'll also say, like, being a parachain, our consensus model is different than Ethereum. So it's not proof of work. That's sort of like the main difference. And so while the EVM and the off-chain tools and all of that stuff will work the same, one thing that you always have to keep in mind when you're working with proof of stake instead of proof of work is that there's really no probabilistic finality heuristic. And what I mean by that is, like, in Ethereum, you can say, okay, my transaction is 8 blocks deep. That's pretty final. Or it's 10 blocks deep. That's even more final. But in a proof of stake system, you don't have that. You have deterministic finality that basically takes a step jump all at once. And what that means is that you can't, 8 blocks is no better than 7 or 6 or 5 and no worse than 10. The only thing that matters is whether you have finality or not. So that's one other, like, small thing that's a little bit different. Good question. Thanks for asking.
Okay, yeah, thank you. So yeah, let's continue with you. Let's go to the next part, probably. Yeah, precompile. So
all right, thanks, Ricardo.
Next.
Yeah,
Thanks.
Sounds good. Yep. So let me spend one commit talking about some standard precompiles to sort of prime the pump, and then I'll get on to the main meat. So, okay. This commit says introduce some standard precompiles, and it adds a few dependencies on crates that write precompiles. So there's all these, they're called simple, and then there's one called modexp, which is for modular exponentiation. And in our runtime, I've gone back and I've once again modified Pallet EVM's config trait. So this time I've changed the precompiles from being unit, which means there are no precompiles, to including all of these standard Ethereum precompiles. So you have like EC recover to get the account that signed a transaction, and some other cryptographic ones, the modular exponentiation, etc. There's really good reasons to have these. Specifically, you can do these things pretty performantly in native, but they would be prohibitively expensive in terms of gas cost on Ethereum. And that's also true in Substrate with executing in a WASM environment. So those are there. And these ones that I've listed all come with Frontier, and anyone can install them with just these 10 lines of code or however much it is. And I've even put a link here to the Go Ethereum implementation. So if you're ever curious, like, what are the standard ones on Ethereum at each hard fork, you can go see that in Go Ethereum by following this link. And at that point, you basically can compile them and use them, and they work just like they do on Ethereum. So maybe I'll just do a quick demo of that. Back in Remix, we already looked at my incrementer a lot, but we now have this modexp contract that we can look at. And I did not write this one. You can see I took it straight off a Stack Exchange, at least the core function here. And this precompile, like most of the standard Ethereum precompiles, can only be called from Solidity by using inline assembly. Whether this is a weakness or a feature is kind of up to your perspective, but as a person who knows Solidity but not EVM assembly, I think of it as kind of a hindrance. But luckily, Stack Exchange had my back. And so what I'm going to do is basically just deploy this contract that makes a few simple unit tests about our modular exponentiation. And as you can see, this one I said is like a wrong example. We're going to start by commenting that, and then later we'll uncomment it to make sure that it does what we expect. So let me compile that contract, and then we'll come down here and we'll deploy it. Now, caution, you always have to go to your injected Web3 provider here. Okay, sweet. And it tells me I'm on network 1337. That's good. And we're going to deploy from Gerald. And I think that might be enough gas, but let's just see. Deploy. Okay, and we'll confirm it. Okay, cool. And it went through and we got the check mark, and like, that's pretty much all we can see, but honestly, that's all we expected. And what that means is our constructor ran without anything panicking. That means that our modexp precompile really is installed, and it really did compute 3 to the 5th mod 7. And then just to, make sure that it works both ways, we'll recompile and we'll redeploy. Oh yeah, and this is actually the first sign that it's not going to work. We can tell already when we're trying to estimate the gas that that's not going to work, but we'll just go ahead and do it on chain anyway, just to be 100% sure. And there you go, that one failed because this is not a correct modexp result. So now we're using standard Ethereum precompiles. But this kind of gets you thinking, like, if there's all these standard Ethereum ones, maybe we want to do some cryptography that's not done on Ethereum yet. Like, for example, maybe for the Grandpa Bridge gadget that we heard about yesterday. And then it gets you thinking, like, really, the sky is the limit. I can express anything I want in Rust, and I don't see why I couldn't expose that to the EVM as a precompile. And this observation turned out to be the solution to one of the biggest mysteries that Moonbeam was facing, which is, if we want our users to use all their standard Ethereum tools like Remix and MetaMask, etc., in order to interact with our chain, how do we square that with the fact that we have like an interesting parachain staking palette and Parity's democracy palette, which can't be used through the EVM? And our answer is we'll write precompiles that wrap around the palettes that are in our runtime. And that allows anyone to use them through a standard Solidity interface with MetaMask or whatever your favorite Ethereum wallet is. And I'm going to demonstrate that technique right now. Oh yeah, I got a little behind my slides. This is where we added the standard precompiles into the runtime. And we did the demo. Okay, so these next two commits are going to show how we write our wrapper precompile and then a little hack we have to do in the Genesis config to make it work. So here's our architecture diagram. We're going to add one more precompile, the template wrapper. So I suspect everyone here is familiar with the palette template that comes with the Substrate node template. It's probably the first palette you learned to write. I know it was for me like a year and a half ago. And it basically just allows a user to store a value and then fetch that value back off of chain. And that's a really good, simple palette to use as an example for our like this wrapper precompile technique. Yeah, so let's just go to the code. All right, so we are now up to this one, palette template precompile wrapper. So we take on some dependencies here. One is FP EVM, that's another Frontier crate, no big deal. One actually comes from Moonbeam, so you can see this one is not part of Frontier, and it's called precompile utils, and it's a bunch of utilities that my colleagues, Jeremy and Eloise, and sort of all of us, but mostly those guys, have written to make this process of wrapping our palettes with precompiles a little bit nicer. Now, our goal is to upstream these into Frontier at some point, but they're still under pretty active development. So for now, they're in Moonbeam, and when they're ready, we can upstream them. Now, whenever you go to take a dependency from a new repo, you got to remember what I said at the very beginning. It's all about the branches. If you don't get your branches squared away at the beginning, you're going to have nasty compile errors, and it's going to be a sad time. So you can see I prepared a branch that makes our precompiled utils work. If you're following this workshop, you're welcome to use this branch. But if you do this in a month with a newer version of Frontier, you're going to have to do that again, or ask me and I'll probably do it for you because I'm really excited for everybody to use these. But you can't not do it. That's the point. And then finally, we need num enum, which is just another crate that you can install. So let me start by showing you this. This is an SOL file, a Solidity file. And we define an interface that I called palette template. And when you're an Ethereum user, whether you're calling this thing directly from MetaMask, like I'm going to do in our demo, or if you're writing a contract, an in-EVM smart contract that's going to interface with this palette, this is the only interface you need to know. You never even have to look at a single line of Rust code. You can just pretend like this is a real Solidity smart contract that someone deployed. And so you can see we have a wrapper for our one dispatchable function in the template palette. And then we have an accessor. Oh, and this could have been, oh, it is marked as view. Yeah, that's good. So that's it. That's our Solidity interface. And now the question is, how the heck do we implement that in Rust to actually satisfy this Solidity interface? So, and here's another thing I want to say. This is better than what they did with the standard Ethereum precompiles like modexp. Since we're satisfying this interface, you don't have to use inline assembly. You really can just call this from Solidity by calling like palette template.do something in your very own smart contract. And for the template palette, maybe that's not that inspiring, but think about this for parachain staking. Moonbeam now supports in-EVM DAOs that can interact with their staking, just like if it were a contract, or political party DAOs that can interact with our governance, just like they were first-class citizens with Polkadot.js keys. So, okay, in our runtime, I added a new module called precompile. I used the precompile struct that I wrote there, and then I added it to our list here. So in the runtime, that's pretty easy. And I made this comment about the indices here. It says that the addresses start at 1 because that's how they do it on Ethereum. But then I made a really stupid mistake. I said that ours is at index 6, but if you just count 1, 2, 3, 4, 5, 6, 7, duh, it's at index 7. So sorry about that. We'll just keep it in mind. Okay, here's the meat of it. This is where we're actually writing our precompile. It's in precompile.rs. So this is the main struct. I just defined a unit struct called palette template precompile, and we're going to implement the precompile trait, which comes from Frontier, for this precompile. Now it has some trait bounds. Obviously, if we want a precompile that wraps the template palette, we need the template palette to be installed in our runtime. And if we're talking precompiles, obviously we also need the EVM installed in our runtime. So that one's pretty clear. The next three all have to do with the fact that we want to dispatch calls into this palette. And so if you're going to do any call dispatching in your wrapper, you can just copy these 3 lines and update it like here, for example. You would put whatever your palette is. And you can look, there's lots of examples of this in Moonbeam. We have wrappers for our own palettes as well as wrappers for Parity's palettes, like Pallet Democracy. And the only method you have to give it here is an execute method. It takes some input, which is just big endian bytes, some target amount of gas. So this is like basically the max gas for this call. And if you run out of gas, it will revert. And then some context from what you called. And this includes a couple pieces of data, but for us, the most important thing it includes is who is the EVM account that's making this call. And that's important so that when we go to dispatch into the Substrate layer, then we call it from the right mapped account. And all we do is basically a match statement on input.readSelector. Now, this is a method that we're calling from our precompile utils, and it makes it very easy to write here, but it does obscure a little bit of what it's doing. So let me just explain it a little more conceptually. In the earlier days of writing these precompile wrappers before we had our nice utils, this would basically say match the first 4 bytes of the input, and then our match cases would be hard-coded like hex literals, and we're basically matching against our function selectors. Remember those 4-byte function selectors like the one we copied for ink? That's all we're doing. We're saying if the 4-byte function selector is the one for the do something method, then call the do something helper. And if it's for get value, then call the get value helper. And I defined these things, I skimmed it, maybe some of you noticed, I defined these things right up here at the very top of this file. Now, if you look at some of our more advanced ones, like our staking precompiles or our democracy precompiles, you'll have a lot of variance here because you'll have a lot of different extrinsics that you can submit. But luckily ours is simple. We have a single dispatchable and a single accessor, so we only have 2 variants. And this, so by the way, the reason you need enum is to use this syntax. And what you're doing here is just in like putting the solidity style function signature, because that's how the 4-byte function selector is calculated. But this is beautiful because all the function selector calculating happens at compile time by the macros. You don't have to like copy them from Remix or worry about getting them wrong in various places. Okay, so that's all the scaffolding. Now we're ready to look at our 2 helper functions, do something and get value. So they all start pretty similar. We make a gasometer. That's how we're going to keep track of our gas. You don't have to use this. This is one of our utils. You can just do manual addition. And in some cases like this one, it's simple enough that that would work fine. But in other cases, it's nice to have a gasometer utility so that you can kind of like put the gas accounting out of your mind. Then we do a bounds check to make sure that our input is the right length. Remember, the EVM is just passing in bytes here, so the input could really be anything. And we want to make sure we have the right number of arguments that we expect. And if we do, then we use our precompile wrapper to parse that data that's solidity encoded into a Rust-style U32. So in the early versions of these precompiles, there was a lot of like you felt like getting out tweezers and picking up individual bits and putting them in the right spot. But now that's all abstracted away nicely into these utils, so that all you have to say is, I know there's an argument because I checked, and I want you to decode it into a U32, and we're good to go. And if there's any error, it's going to be handled gracefully. Okay, so now that we have all of the data, specifically the U32 value that we're going to be stored, we can get the origin. So what we do is we use our address mapping. I looked at that earlier. This is where I said Moonbeam uses the unified accounts. And we convert the caller from EVM world into Substrate address world. So now we have like an account ID 32. And then we construct a call. We're going to call into our palette template. We're going to call its do something method, and we're going to give it the value that we just parsed. And once we have the call constructed, we use this runtime helper. This is another one of those utils that I showed you. So this is all kind of done nicely for you to try to do the dispatch. And if the dispatch fails for any reason, it will be handled gracefully with a nice error message that goes all the way back to EVM world. And if it's successful, then it gives you back the gas that it used, which you can record in our gasometer. So this is really our only gas recording. That's why I said, like in this one, using the gasometer maybe was overkill. But if you have multiple calls, or if you're going to do your own storage reads, the gasometer is for sure something you want to use. Finally, we give back our precompile output. If we made it all the way to the end of the function here, it's really easy. It succeeded. We give back the gas we used. And this one doesn't even have a return value or any logs, so we just put default. The precompiled utils do have the ability to do logs, which basically means like solidity events. And these are really useful because this allows, like, for example, Etherscan or your favorite Ethereum style block explorer to display events exactly like they would as if this were solidity. And when we defined our solidity interface up here, you can even define those events right in here and they'll work exactly the way you want. So that's a dispatchable wrapper. Your dispatchable wrapper will be very analogous. I honestly wrote this by copy pasting one from Moonbeam and just typing over it because they're similar. You know, you always make the gasometer, check your bounds, parse your values, make your call, dispatch your call, do your gas, return the answer. It's always the same flow. And then this one's a getter and it has a flow also. Make a gasometer, check our bounds, none in this case, that's dead simple. Parse our inputs, but there are no inputs, so that was dead simple. Okay, here's where we actually call into the pallet. So this is code that executes inside our runtime, so we can call this stuff directly, just like we would anywhere else in our runtime. Maybe you could do a little more graceful error handling if you wanted to, but I didn't think that was an important part to emphasize today. Here's a little bit more interesting use of the gasometer. Here we manually did a storage read from the database. So here we're manually recording the cost of one storage. And I'm using our runtime helper, so I'm using our util for that. And what this utility really does internally is it looks up the database cost in weight from the runtime, from frame system actually, and then it uses Pallet EVM's gas weight mapping that we talked about earlier to map that weight into a gas, and then we can record that gas in our gasometer. So this one's a getter. This time it actually does have some output, and so we have to construct that output. And this is the case where there used to be a lot more bit tweezers again, you know, formatting bits and bytes exactly the right way. But we have a utility for it, which is really nice. And so we just write the stored value. And look at that. It even does type inference. We didn't even have to tell it what data type this was. Rust just inferred the type, and then we return it. And again, I didn't do any logs this time. Now, obviously, if you're going to do this in production, you should have a mock runtime and you should have a bunch of tests. And here are the examples that I mentioned. But for now, this is going to do it. So let's do our demo. Wait, where is the demo? Back in Remix, okay. So we've looked at our incrementer, we've looked at our mod exp, and now here's our final one, the pallet template. This is the same Solidity interface that I showed you before. Everything's the same about it. It's not a contract, it's just an interface. So I can still compile it, but I can't deploy it. You can't deploy an interface, you can only deploy a contract. But what I can do is tell it there's already an implementation of this thing in my EVM somewhere, and I just have to tell it where. And if you remember, it was at that special address 07. And now I just need to get something that's the right length. So let me just do this little hack. There, okay. I just wanted an H160 that had the right number of zeros so that I didn't have to count it. And remember, the comment said that it was at address 6, but that was a mistake. It's actually at address 7. So I'm just going to say this thing is at that address already. Okay, and so Remix tells me like, hey, I understand that you already have this pallet template contract deployed at address 7. And it is deployed. It's deployed in the sense that there's a pre-compile there. It's actually compiled in. It's written in Rust code. So first, let's get our value. Oh, wait, let's see. Is my thing still running? Let's put a value there first. So we'll go to our pallet template and we'll do something and we'll store a value there. I'll just store 42 so we can make sure if it's the right one. Sign and submit. Okay, and let's make sure that's there. So we'll go to chain state, template module, and we'll read this something thing. Okay, 42, all right, that's all good. So here we are. Let me reset my MetaMask account again. Whoops, that was up here. Just reset account. Okay, all good, and so Remix, yes, we're in, let me just switch that to injected web 3. Okay, account 1337, that's great. This is at address 7. Oh, it didn't take that. Let me say at address, okay. So let's try again and see if we get any more luck. Oh, we didn't get luck. Okay, let's try to store something and see if that works better. 32. Okay, let's submit our transaction. Okay, it went through. So now we can come back over here and, oh, it already updated too. I forgot these are subscriptions. So now it says 32 instead of the 42 that we stored before. And let's just try another transaction there. Okay, that worked. And so, all right, let's try to read it one more time. I guess it's saying out of gas. Maybe it really is running out of gas. Let's just add more gas. I don't really know what the right amount of gas is, but hopefully that's enough. Oh, there it was. Okay, we just needed more gas. So, oh, actually, that makes perfect sense. You might remember I said that I set up our gas weight mapping as 1-to-1, which is not a reasonable value. That's why we have to put in a stupid amount of gas for that call to go through. So, okay. I had like just a few more slides that I'm going to skim at this point. There is this thing, consensus level support. This is one of the least important parts, despite how important it sounds. All this does is allow you to assert that Pallet Ethereum is installed in your runtime at every single block, or the block will be rejected at the consensus level. So if you're going to install Pallet Ethereum via a runtime upgrade, or if you're going to remove it via a runtime upgrade, you actually should not have this installed. But if you're going to do what I said earlier, like try to make an actual Ethereum 1.0 node that will join Ethereum mainnet, then this is critical because you obviously need the Ethereum support the whole time. And then the last thing I'll talk very, very briefly about, but not show, is opcode tracing. This is functionality that allows replaying Ethereum transactions over the same state on which they were originally executed. So think about like, hey, I submitted some transaction 50 blocks ago. I'd like to re-execute that. You can do that with this opcode tracing thing. And the result can be captured, and you can watch each opcode tick by. And this is really, really important for things like Block Scout or Etherscan, or basically any Ethereum-style block explorer. This is another thing like the precompile utils that's being designed in Moonbeam because it's still pretty new, but will be upstreamed into Frontier, hopefully eventually. And a major shout out to my colleagues Telmo and Jeremy for designing and iterating on this over the past few months. This is a major engineering feat. So that is all I have. If there's any questions, I'll take them, but I know we're a few minutes over. So thanks a lot, Ricardo.
Awesome, Joshy. This was a really, really great talk. I mean, yeah, it's always really good to be talking with you. It's amazing how good like all Frontier code has evolved and really, really compatible with Ethereum. Yeah, thank you so much.
Good to talk with you too. Yeah, thank you.